Alright, welcome back for lecture 11. We're going to be going over real measurements, so in other words, some of the factors affecting your measurements. And then we'll examine one-way range, two-way range, Doppler, so in other words, range rate, and finally look at difference measurements, which are very important to us and where we're trying to get to. But first, a little recap, lecture 10, we covered an example to kind of illustrate what was going on. We spent only about 10 minutes on it, but at the same time the code's on GitHub, and I expect if you're watching a video on YouTube that you're going to be a little bit of a self-learner. There are some issues with the code that are tracking. Those, of course, are on GitHub. And, those have been identified so that you can go solve those for yourself if you choose to do so. But the notes are posted there, and any questions, post them on the YouTube page. So, for our agenda, like I said, we're going to cover the environment. Really, we're going to focus on two things: the atmosphere and relativity, and how those affect our measurements. Then we're going to go through some of the systems, so the one-way ranging, two-way ranging, Doppler measurements, what we use to make those measurements. And then finally we're going to go to difference measurements, which is really a method, but at the same time it's what we're leading up to because we want a difference between the observed and the computed and have two receivers and get better estimates so that we can reduce our residuals, because the whole point is to reduce your residuals so that you can reduce the error in your position and your velocity. So we're getting there. So we're going to start off with the troposphere. So the troposphere, it's refractive to radio. There's a delay, and we still call it the troposphere delay, even though the stratosphere contributes about 20% of that delay. So if you take delta rho, where it's about 10 to the negative 6th, where n is the refractivity, we can model that refractivity. And so the dry refractive component contributes about 90% of that delay, whereas the wet contributes about the other 10%. And so obviously the atmosphere's refractivity is going to change, and that's a linear term, so that you can add the dry refractivity and the wet refractivity to get the total refractivity. The troposphere is dispersive to optical as opposed to refractive. And again, it's dependent on elevation. So what that means is that the longer it has to travel through the troposphere, the more refractive, or the more that the troposphere is going to affect the signal or disperse the signal. So think of it in terms of if your elevation is low, like 5 degrees from your ground station, as opposed to directly overhead, the satellite that sends that signal is going to have longer to travel from the satellite if it's all the way out at 5 degrees elevation as opposed to directly overhead. So we said it's dispersive to radio. Oh, excuse me. This is actually for the ionosphere. So ignore the top line of this. I'll fix this for the website, but the troposphere should be should read ionosphere. The ionosphere is dispersive to radio, and there's no significant effect to optical. Now, why is that? Well, for optical, the mean free path is so large that it's not going to be dispersed by running in the photons running into all those particles. However, for radio, there's a large ionic magnetic component. So in other words, not really necessarily magnetic, but ionic, where there's free electrons and other charged particles in that region of the atmosphere that will affect the electromagnetic wave that's propagating. In other words, the radio wave around that frequency. So that'll mean that if we take the delta T, where essentially alpha is the total electron content and F is the frequency being transmitted, then that delta t is going to give us some dispersion, or at least the idea of the delay that we're going to see from the ionosphere. The other neat little trick about this, because it's actually dispersive, it's not the ionosphere. So this is a little tidbit, right? So amateur radio guys, they'll bounce signals off the atmosphere, and what they're actually doing is they're bouncing signals off the troposphere as opposed to bouncing it off the ionosphere, because if they shoot all the way through the troposphere, it's going to be dispersive in the ionosphere as opposed to refractive. So, anyways, again, the delay is dependent upon the total electron content that's present in the ionosphere. That's temporal and spatial. So, in other words, the South Atlantic anomaly, which go Google it, it's a fun little tidbit, but because the Earth is rotated, the Earth's ionosphere or magnetosphere is actually not rotated with the Earth, so the South Atlantic anomaly is actually where some of that magnetosphere carries some charged particles directly into the Earth. So when the ISS passes over the South Atlantic anomaly, astronauts are actually exposed to more electrons and charged particles than than they otherwise would be. It's something that Johnson Space Center has to keep track of for their astronauts. The ionosphere, for most purposes, starts at 80 kilometers upward. There's 4 different phases or 4 different regions, but they're not as clearly defined as the troposphere and the stratosphere. But yeah, it's an interesting read. One of the good books out there is by Biscayne on the space environment. So go to AIAA. Biscayne has a book on the environment. He's written a bunch of papers. It's basically a collection of his papers and his work on the environment. It's a good read. It gives you a lot of good background information. So some of this is derived from this. The book that we're using, the statistical orbit determination textbook, actually draws from Biscayne into the book. So just for your reference. So the other portion of the environment that we have to consider, relativity. So general relativity, we know that if the satellite's passing overhead, because of the speed at which it's traveling, the clock on the satellite will actually pass slower than the one on the ground. So if we have a circular orbit, the clock may beat faster or slower than the ground, and that's dependent upon the altitude. So the technical term, a satellite experiences relativistic precession of perigee. The clock varies with the same orbital period when we have a non-circular orbit. So it still varies about the mean frequency of that orbital period, not of the orbital period, but it still varies about that mean frequency that we're transmitting at, but we have to consider some time offset correction because of the transmission from that moving object, and then there's a time delay caused by the Earth because this Earth is this big, massive body that can bend light waves, right? We know from recent events, drawing in now that we're recording, I can take advantage of it, but recent events, taking a picture of the black hole. What does a black hole do? It has such massive gravitational pull that it literally bends light, right? Same idea. We have a time delay caused by the Earth from our signals that we have to take into account. And we're ignoring the Sagnac effect because it's our only concern with that is when we're passing high precision clock information via. So if ground station here passes information to satellite and then down to the ground station, then we would be concerned with that effect. We're not going to consider that in the course of this text. That's actually kind of outside of the scope of what we're trying to do, which is lock down the position and velocity with high accuracy of a particular satellite, as opposed to looking at and just knowing where our errors arise. So that's a little out of the scope, so we're going to ignore that for now, but feel free to look it up on your own if if you want to. So now we'll step into some of the measurement systems. Today we're only going to be covering the one-way range, and then we'll move on to two-way, looking at the Doppler, and then finally we'll go to difference measurements using some of these systems. And so what these are is I'm going to talk through some of the systems out there that do the measurements that we've talked about. So, for instance, GPS, right? GPS is a constellation. There's 6 orbital planes with an inclination of 55 degrees. They all have about the same orbit of, about 12 hours or so. And there's 3 civilian frequencies used that have a fundamental frequency of 10.23. They transmit on the carrier frequencies of 154, 120. And then finally, the third most recent frequency is L5, so at 115. We have a pseudo-random noise that's transmitted as bits over the carrier, which is our coarse acquisition code that's transmitted at 124 bits at every millisecond. That cycle repeats, and so that is where the idea of a 10-meter radius for where we actually are comes from, because if we're receiving only L1, right, then we can get that coarse acquisition, but we may have issues getting the carrier phase, so we can only get about a 10-meter resolution of where we actually are. But if we're able to acquire the coarse acquisition and we're also listening to another one of the bands, then we can acquire the carrier phase. And then the carrier phase, we're able to, each one has a week cycle where each GPS satellite is on a different week, but there are 37 weeks spaced out between them, or 37 weeks for the repeat each. And so from that carrier phase, we're able to reduce that down to sub-meter level, talking centimeters, as far as where we're located. And then finally, the third signal that's superimposed upon those frequencies is the Y phrase, or the Y signal, which is essentially a mix to prevent anti-spoofings for military applications. Obviously, since this is on YouTube, we're not worried about this, but that's the third frequency. There's P, Y, and CA, or in other words, coarse acquisition, right? Typically, we'll try and have some cross-correlation between some simulated signal on the ground and the received signal, so that we can compare the residual to that and try and map out where we actually are. Yeah, let's move on to the next slide. Like I said, pseudo-range, we can get our pseudo-range measurement from L1 or from just using L1 or L2, but remember, this is one-way measurement, so we're going to have to consider the clock errors in the receiving and on the transmitted side, passing through the troposphere and passing through the ionosphere, along with some known error. In practice, we may not know this with high accuracy, but getting a true range requires that we have the true GPS position and receiver coordinates along with that true time. So it may not be known with high accuracy in practice, but ideally we'll generate enough measurements over time in order to reduce that residual to the point where it's a good enough measurement for our particular application. Carrier phase, obviously, like I said, gives us a more precise measurement. It's a one-way measurement. So if you remember from our Doppler shift, the wave times N is the integer phase ambiguity, and really that's what we want to solve for, because we measure the phase range that we see, and then if we solve for the phase ambiguity by using multiple signals, then we're going to be able to get a very precise measurement on the order of centimeters. So that's all I have for today. Again, it's very quick, but we'll turn around and we'll cover the two-way range, or some of the two-way range systems that are out there, some of the Doppler systems that are out there, and then finally talk about differenced measurements and how those are very important to what we do with orbit determination. So thanks for watching. See you next time.